Hello, everyone. Thanks for coming to my talk on text mining with Node.js. My name is Philipp Burckhardt. I'm a fourth-year PhD student at Carnegie Mellon University, mostly working in computational statistics with applications in healthcare and education. But what brought me here more is my alias, Planeshifter, who's quite busy working on NPM modules for statistics, text mining, and other things. Text mining and Node.js is not something you usually hear in the same sentence, I would say. In fact, one might raise the question if not statically typed, compiled language, such as C++ or C, would be more appropriate because of the obvious performance benefits. And in case of really large data sets where you have like hundreds of thousands of documents, that's certainly a valid argument. But let me tell you from my domain, like in statistics, for example, there are many other considerations that people have besides speed. For example, the majority of statisticians use this programming language called R to do their analysis, and this language is actually horribly slow. But R has the advantage that all the statistical methods people have implemented basically in R. So, and if a statistician wants to do text mining, he or she would probably ask himself, okay, why we invent the wheel? I can just do it in R. So, and I think similarly that there are some valid reasons why we might want to do text mining applications inside of Node. And I can think of at least 4 that I would like to outline. The first being that JavaScript is the language of the web. So with WebAssembly, now other languages might target the browser. But if you want to run anything inside the browser, then certainly JavaScript is the way to go there. Also because we can basically target any platform. Like with browser-defined Webpack, we can bundle our code for the browser. We can easily write Node command line applications or desktop applications nowadays with Electron. So if we have some text mining that we want to do inside of our applications, being able to do it, write it once, and then have it on all platforms is certainly like a big benefit in my opinion. Thirdly, the V8 engine of Google, which powers Node, is actually fast enough to handle like reasonably sized text mining applications. And that's in stark contrast actually to Python or R. So if you look at the popular text mining packages in Python and R, they all basically call down to C or C++ because the languages themselves are just not fast enough. So if you want to avoid kind of that language switch or that context switch, being able to just run everything in one language, it's actually a pretty nice thing, and you can do it with JavaScript inside Node. And fourth, I think the Node streams package is really great to build like data pipelines if you want to do handle text data streams. And there we also don't run into the memory issues that you might get into if you do batch processing like of large documents collections. I think one big drawback is that just the ecosystem is not really there. There are a few packages like that are popular and like, for example, Natural by Chris Umble and others, but there's just not a big ecosystem of text mining modules. And so many things you would just have to code up on your own. Just to give you an example where I personally encountered that choice, we were confronted as part of a research project with the task of de-identifying patient data. And this is required by US law, so I thought there must be like many open source software solutions which actually do that. But I just found some abandoned projects written in Java, Python, and other languages, but they were not really supported anymore. So the best way forward just seemed to build this tool on our own. And we did it with Node.js, so kind of the predecessor of Electron. And so being able to basically build a tool that now anybody, even without like any technical knowledge, can use if he or she has to de-identify such confidential information. And to make this a bit more concrete, here's an example, like a little screenshot for like how you can process a single file in this app. Just drag a file on there, and then the text mining aspect is basically that we have a model which detects our personal identifiers. For example, here, John Doe, this person on the left, and we replace it by like an automatically generated fancy identifier. So here, John Doe becomes Leila Rice. Now, that might be pretty neat or not, but when you delve into text mining, I think you will often face this challenge, namely that text data is incredibly messy to begin with, especially if you compare it to more structured data that usually store in a database. And I think there are some philosophical reasons for that. One being that words have different meaning, which one calls polysemy. Also, words are often their meaning depends on context, is ambiguous. But even on a very basic level, one confronts just some tricky and cumbersome tasks, like splitting strings into sentences where you just cannot just split by dots, right? Because people nowadays use emojis and stuff like that. Or tokenizing a string into different words where you need to account for punctuation. And so you, again, cannot just simply split on white space. So the first thing you always got to do if you work on any text mining project, I would say, is cleaning up your data in a sense and get it into a shape that you need for your type of problem. And I don't think there's any general way of how to do this, but really depends on your given problem that you want to solve. But why do I think this is rewarding? It is estimated that unstructured data, and that's mostly in the form of free text, accounts to roughly of 80% of all data that is collected. So given in the example of the medical sector, so people who have been doing analytics or data mining usually just looked at this tip of the iceberg, kind of the numeric values, like lab values of patients, etc. But now, more and more people are aware that the real treasures might lie underneath the water surface in that sense, where you have doctor's notes, discharge summaries, etc. And I'm pretty sure that in many other industries, the situation is kind of similar. So now, instead of giving a full overview of text mining techniques, which would kind of be infeasible also given the length of this talk, I will just present two basic applications, just two basic techniques, and we will look at how we can use those or implement them in JavaScript. So first one is sentiment analysis, so pretty basic one. Basically, we want to analyze whether a text expresses, so to speak, a like or dislike. We could analyze film reviews and find out whether the new movie by Woody Allen is looked favorably upon by film critics or not so much. Similarly, we could analyze Twitter feeds, looking at whether the Twitter population looks favorably upon Donald Trump's latest outbursts or not. So the other application that I want to highlight is kind of cluster analysis and topic modeling. So this is a problem which requires often kind of more sophisticated models. And but let me first try to explain. So imagine you have a collection of documents, for example, newspaper articles. And in a newspaper, you have various sections, right? So you have the sports section, you have celebrity news, politics, etc. And basically, now imagine that instead of having a human who categorizes these texts into different categories, we want to have a computer algorithm doing that for us. And so the computer obviously doesn't understand anything about the difference between a soccer game or a Paris Hilton shopping tour. But so how can we teach the computer in a way to group these data into different categories in a plausible way? And what many of the statistical methods for this task do is kind of pretty simplistic. They treat documents as a kind of bag of words. So basically what one does is one just treats a document as a collection of words, get rid of the whole order in that sense. And then what kind of a topic then is just a co-occurrence of words. For example, in a sports topic could be, we would have, even for different sports like tennis or soccer, some words will appear with high frequency, like score, and someone has a win, points, loses, game, etc. And so these words kind of will link these documents together. And now, basically, it's just the algorithms work by exploiting that co-occurrence of words and trying to find an allocation of the documents which makes kind of this most probable. Now, but without enough of these preambles, so let's get a bit more practical. So the first example I want to give is of sentiment analysis of State of the Union addresses by President Obama. So the State of the Union address is an annual speech by US presidents in which they reflect upon the state of the nation and in which they talk about their priorities and future plans. So here's a bit of code. first, what we do here is we load these speeches. So this module, standlib, this is a module that I'm involved in, and it's still very much work in progress. If you're interested, you can find it on my GitHub page. You would need to check out the dev branch, though. So what we then do here is we also get a word list, this FN word list here, which is basically an array of arrays, and each array element will be a word where we have like a valence score from -5 to 5, depending on whether this is a positive or negative word. And then we also get this tokenizing function to just split a text into white space, into its individual tokens. Now, the first thing we then do is let's here create a hash table, just turning these words so that we can have a fast lookup, being able to just, for any given word, find the associated score here. And that's one thing I really learned the hard way. When you do any of these type of tasks, you really want to think about the types of data structures that you use and the types of algorithms. Because imagine, like, even if you have only 1,000 documents and each 1,000 words long, it's still like then you have already 1 million things to iterate through if you do that, for example. So you really have to think about, okay, you want to avoid searches, like how do you efficiently implement things? And so, okay, what do we do then here? We get these speeches of Obama, and then we do like this pre-processing that I talked about. So that's like often the case. So here these speeches are just basically an object array. Has some other attributes. We are only interested in the text right now. So what do we do here? We just get the texts. We then turn them all to the lowercase and we tokenize them. And I kind of didn't follow my own advice here because, like, in general, I would advise against using the array prototype methods, because this, like, again, if you have like really large arrays, the function context that it's created, like this, will eat up a lot of memory, and so you will run into problems quite soon with, like, as your data sets grow. So I mean, in this case, we have only 8 speeches, so it's not really a problem. But in general, like for loops, like the basic construct would be much more feasible for that type of task. So then we just simply here allocate an array. We want to calculate the sentiment for each document, and then we just calculate the cumulative score for each document. And that's a really simple method, right? A really basic method. What do we get out of it? We basically get this array of sentiment scores, which we can look up here, from 2009 to 2016. And I think some things one can really rationalize here, right? We see first 2009, 2010, we have still like really low, like a comparatively low sentiment score, which kind of makes sense given that it was kind of in the aftermath of the financial crisis, and so the recession still was hit hard. And here we might have, like, this might also be interesting looking at the different words that are associated with that occur in these speeches, like the positive and negative words. So we see the negative ones mostly like recession, like the wars the US is involved in, and on the good side we have like things like good, etc. So here one has to be aware that we cannot really, with our simple method, right, we cannot handle things like irony, negations, and ambivalence. So like in Shakespeare's Julius Caesar, like when Mark Antony gives a speech about Brutus, might get a high sentiment score because he refers to him like as an honorable man, but it's basically just it's a sarcastic, it's a total annihilation, attack on Brutus. So we might not get that with our method here. So that's what I want to talk about with respect to sentiment analysis. The other thing, topic modeling. So we thought about what's the goal. The goal is we want to find documents which share kind of the same themes and identify those themes, be it like politics, business, or sports, or whatever the domain is. Like one of the most popular methods for doing so is called latent Dirichlet allocation, which is a probabilistic method that was developed by Bly and others in 2004. And what it assumes, like the basic assumption is that a document is represented as a distribution over topics. So that's what differentiates topic modeling from clustering algorithms. So you might have come across like k-means clustering, right? For example, where the assumption is that any observation belongs to a single group, like we just But here in these type of models, the assumption is that any individual document is kind of a mixture, has different proportions of the different groups. And why that makes sense, you can imagine that, for example, like an article about David Beckham might be like both like a sports, but it also might be this celebrity like Paris Hilton topic. So, and there's no clear-cut distinction often. And that's why these types of methods usually work much better on text data than like something like clustering algorithms. And this particular method has become really popular because it's easily expandable, and so many people have kind of developed variants of it for any given problem. So now let's look at what we do here. So here's a simple example again where we use this in JavaScript. We again use our corpus of speeches from presidential elections. This time I also get some like another word list here on top, like these stop words in the second line. So that's basically stop words in text mining denote like high frequency words that are like pronouns or conjunctions like the, and, etc. So all these words which do not have any significant meaning on their own. And in some contexts, you just want to remove those. For example, in the sentiment analysis case, it didn't really matter because they might not get a score anyway. But here in this case, it matters because what we will do is we will represent a topic by its most probable words. So in that sense, if there are some words which are so frequent that they appear in kind of in all topics, then this would kind of obfuscate our results a bit. And so we rather remove those at the beginning. Besides that, we load this LDA latent to a clear location module here, and then we proceed similarly as before. We tokenize our texts, and then we here now keep only the words which are not in the stop word list. And then we create this LDA model. This function here takes like two parameters. First is like an array of documents, and the second is the number of topics. So in this type of model, you actually have to specify like how many topics you want in that sense. And there are some criteria that you can use to choose like an appropriate number of topics, but what people often do is they just run the algorithm for different numbers and look for kind of what's most sensible. So it's still kind of debatable what's best in that sense. And then we just fit this algorithm. So here are some parameters which basically decide how many iterations we run here. So let me show some of the results of this. So for the speeches from 1930 to 2010, we said we wanted to have 3 topics. So and these are the high probability words for each of them. And so I think at least like the first and third topic, they have a clear theme. The first seems to be mostly like military interventions, wars, etc. And the third one seems to be mostly like government programs and economic programs from the government. And what now is interesting to look at how the different speeches are made up of these different topics. And we can look at this over time, right? Because for each year we have one speech. And I found it's like the war one is pretty reasonable, I think. So we see that here, right, in the Second World War, that it spikes, and then we see also like Korean War, and then now in the 2000s after 9/11, there's another like spike in that topic proportion. But some of the other ones I was kind of surprised in a sense, because I would have imagined that mostly there would be like differences across the different political parties, so that when Democrats or Republicans are holding office, that we would see differences. But it seems like more like a time trend here. And the time trend seems to be that this topic of government programs and government interventions really, in the 1930, it was like almost like the whole speed, like 90% here, and it goes down to less than 20%, or like 20% in the last years. And so that kind of really, I think, shows that like after like the worldwide recession in 1929, like there was like the New Deal, so lots of government programs to aid the poor, and that seems to be like have kind of disappeared in the talk about that. And this coincides with the rise of the green line here, and this is more like a topic, I think, where it's about like tax cuts and healthcare and balancing the budget and all these things. So my guess would be that this kind of attributed to kind of the win of neoliberalism in the sense that now cutting expenses and that government efforts to aid the poor are not that big of a discussion in the United States anymore. So with that, I would like to close. Hope I gave you some ideas of what typical text mining applications are. I'm free for questions, and I'm around also, so if you want to discuss anything, please let me know. Thank you for your attention.